Great. Thank you. So I'm supposed to talk into two microphones at the same time. This is going to be interesting. But yeah, thanks for coming to my talk. My name is Tim Sweetser, and I'm a data scientist at Stitch Fix in San Francisco. And I will be talking about mixed effects models in Python. So I'll give you a little bit of context and motivation, tell you about Stitch Fix and the sorts of problems that I work on there. I will go over what mixed effects models are and how they can be used for some generic recommender system kind of problems. I will go into the computational considerations of these models. And then at the end, I will talk about Diamond, which is a Python package that I wrote with my colleagues at Stitch Fix for fitting these kinds of models. So Stitch Fix is an e-commerce company. And bear with me here. There we go. Stitch Fix is an e-commerce company. Customers come to our website. They give us some information about their style preferences and how old they are and their size. And we take the information they give us. We combine it with information that we have about our merchandise, the clothes that we have in inventory, such as the color of the garments and the material. We combine these and do some machine learning, and then we make suggestions which are consumed by human stylists. So the stylists look at our recommendations, they pick out 5 things, they get mailed off to the customer, and customers keep what they like and send back everything else. So the part that I work on is what I am calling algorithmic recommendations here. So for the purposes of this talk, it's a pretty standard recommender system kind of application where we have users who see certain items and provide some kind of explicit feedback on those items. So let's get into a little bit of math. So the straw poll I conducted a few minutes ago, most of you identified as data scientists, so I'm assuming that you are familiar with the linear model. So I will just give you a brief refresher. Suppose that you have gone out into the world and observed some data. And one of the things you have observed is special. You have this variable y that you wish to explain in terms of some x's. So a very simple place to start is with a linear model. And you posit that your y variable is just a linear combination of your x variables. And there's some noise in the system. And what you want to do is find this, this vector of coefficients, beta. Okay, I'm sure everyone in this room has fit a linear model before. So a mixed effects model builds on this by adding a second set of coefficients and a second design matrix. So before we had x and beta, which we still have. And now we have another matrix and vector of coefficients, z and b. And z can have some of the same columns as x, or different columns. In general, you can put whatever you want in there. But whereas the betas are unknown but constants, the b coefficient vector is considered to be drawn from a normal distribution, centered at 0 with some unknown covariance matrix, sigma. Okay, so that's the basic math of a mixed effects model. Let me give you an illustration of why such a model might be useful. So I work on clothing, primarily women's clothing. And let's suppose that you want to learn some relationship between the ideal length of women's jeans and how tall the woman is. So you start with a linear model and say that I think the right length for the jeans is going to be some intercept plus something proportional to her height. So taller women should have longer jeans, and then there's some intercept that you start with. But this is not enough, because you also think that the jeans might need to be longer or shorter depending on the silhouette. So if they're skinny jeans or wide leg jeans or straight leg jeans, the the genes might need to be longer or shorter for a woman of the same height. And the reason this might be the case is this reason. So the model on the left is wearing skinny jeans, and you can see that they end at about her ankle, whereas the model on the right is wearing bootcut jeans with heels, and these extend down below her ankle, halfway down her foot. So if these models were the same height, the skinny jeans would clearly need to be shorter than the bootcut jeans. So let's think about how we might fit the simple linear model, the one that ignores silhouette. So we're going to model length as our X matrix times our unknown coefficients beta, and a row of our X matrix is going to be, we're going to have an intercept, so that's the first column of X, and then the second column of X is going to be the woman's height. So this row that I drew randomly, this woman is 5'4" tall. And we can fit this model if we have some data on how tall women are and how long are the genes that fit them well. And we could use something like stats models to, to fit this model to our data. And stats models uses formula notation. Are people familiar with formula notation? Some nods, some no's. Formula notation, so I guess this is on the bottom of this slide, I have the mathematical notation. Formula notation just says, this is my response variable, and I want to fit an intercept plus height as a linear term, and I want to fit this model using this data. So people who have an R background are very familiar with formula notation, but it's used in some Python packages, such as stats models. And the package that we wrote, called Diamond, also uses formula notation. And if you fit this model, what you get is this nice straight line with the intercept and slope parameters that you learned. Okay, so then mixed effects, you can also fit this with stats models. And we start with the same part. The initial formula is the same. We're going to explain length with an intercept plus some slope on height using the same training data. And then we're going to fit an intercept for each silhouette. And then we take that and run. And what that gives us is this set of parallel lines. So I have kept the overall average in black here. And what we have done is allow the different silhouettes to have different intercepts. So we can see that indeed bootcut jeans need to be a bit longer, whereas skinny jeans are a bit shorter, and then straight leg and wide leg jeans are somewhere in the middle. So we have learned that indeed there are some differences in ideal length by silhouette. So how did we learn this? Let's go back to the math. I said before that our model in mixed effects, it has two design matrices with different coefficients. So our X matrix, as before, is just a column of ones for the intercept and height. And our Z matrix, because we're only interested in fitting an intercept for each silhouette, our Z matrix is going to be just all ones and zeros, but strategically placed. So imagine taking our data and sorting it all by silhouette, so that all of the pairings of women and her height and the length of the genes, all of those observations for bootcut genes are at the top, followed by the observations for skinny jeans and straight leg jeans and wide leg jeans. And then we basically repeat the first column of our X matrix, in other words, that column of ones for the intercept. We repeat that in Z only for those observations that it is relevant for. So in other words, for the bootcut observations, we have a column of ones and then zeros everywhere else. Likewise for skinny, likewise for straight and wide leg genes. And this gives us our original X design matrix was n by 2, and now because we have we're fitting one parameter, and we have for each silhouette, and we have 4 silhouettes. Now we have an n by 4 design matrix Z. And we'll learn different intercepts for each of these. So yeah, and the key assumption here is that each of these intercepts is drawn from some normal distribution centered at 0. And the amazing thing about mixed effects models is that it learns this, this variance parameter. So in practice, what this means is that groups that are small will get pulled towards this normal. This is sort of like a, if you're familiar with Bayesian statistics, this is sort of a normal prior. And what this will do is, for small groups, it will pull them towards the mean, or towards 0. So if we have, if one of our groups is much smaller than the other ones, in this example, wide-leg genes are not very common, so we don't have very many observations for them. So even though they might have a very different relationship between length and height, this regularization will pull them towards the mean and not let them stray too far. And the way this happens is because we're including an intercept for an overall intercept, and then we're regularizing deviations from that overall mean. Okay, so that's an example using a simple example of sort of how mixed effects models work with a little bit of formula notation and math. Let me give you another example of mixed effects models for a more generic kind of recommender system. So again, this is a scenario where you have users and items. Users see some items and provide some kind of rating of those items. So a very, very basic model you might start with for a recommender systems problem is it just fits some kind of global mean, and then you have a bias term for every user and a bias term for every item. And you assume that the bias terms for users are drawn from some normal distribution with some variance, and likewise for items. And this will let you learn stuff which is, learn things which are very common in recommender system problems, which is that some users are more picky than others, and some items are much more popular than other items. But because mixed effects models are built on top of linear models, it's easy to throw features in. So you could add in some item features to the user group. And if for a clothing application, this could be features like color and material. And that would allow us to learn like individual users' preferences for different characteristics of the items. Or we could put user features such as age into the item group. And that would allow us to learn whether certain items are more popular with younger or older clients. Again, we assume that our coefficients are drawn from now multivariate normal distributions centered at 0. Using features is great. It allows us to learn the preferences I just mentioned. It also helps with the cold start problem for new items and new users. Unfortunately, if we have 3 features in here, an intercept and then 2 item features, we have to learn a 3x3 covariance matrix. And in general, if we had p features, we would need to learn a p by p covariance matrix, which scales as p squared. So that is not so good. I want to make a comment about this model, which is that we have we have come a long way from the simple linear model. So now we have lots of features, and we're learning a lot more. But this is still a parametric model, and much less flexible than other kinds of models, like neural networks or matrix factorization or tree ensembles. But I don't want you to think that I'm claiming that mixed effects models are better than any of these. I'm not claiming that in any way. you can use mixed effects models in combination with all of these other things and fit them all and then ensemble them or use boosting or however you like to combine models. I think that mixed effects models deserve to be one of the tools in the data scientist toolkit. Okay, let's address the computation of these models. At Stitch Fix, for a long time, we were using R, and we're using the LME4 package, which is based on maximum likelihood, which is the traditional statistical estimation procedure. And for these models, the computation goes like this. We start with some estimate of the covariance matrix sigma. Given that, we can compute estimates for beta and b, all of our coefficients. And with all of this, we can compute the log likelihood. And then we can go back and adjust our estimate of sigma to increase the log likelihood. And we just loop through these until the whole thing converges. Unfortunately, this does not scale well with a number of observations. I don't know what the big O performance is off the top of my head, but I have some empirical results that will convince you that this is true in a couple of slides. LME4 is nice because it supports a variety of generalized linear models. So you can use it to do not just linear regression, but logistic regression or Poisson regression or a bunch of other flavors. But its generality means that it's not optimized for any of those in particular. The other thing is that a lot of our production models at Stitch Fix, we think it's important to refit these models frequently because we think that the parameters are non-stationary. In other words, they change over time. But we're willing to assume, or we think that our hyperparameters are more stationary, or at least that they change more slowly. So if we're refitting models every day, it seems unnecessary to refit the hyperparameters every day. It seems like it would be adequate to fix the hyperparameters, freeze them for a while, updating the coefficients beta and b, and then once in a while update the hyperparameters. So to that end, we wrote this package Diamond. So it does not do all of the things that LME4 does. In particular, it does not learn this hyperparameter covariance matrix sigma. You have to input sigma. But the nice thing is that conditional on that, the optimization problem of finding the coefficients is convex, which means we can use some tricks from convex optimization. So some of the tricks we use are the Hessian of the penalized log likelihood function. And this involves some pencil and paper math, so we only did it for the models that we use a lot, in particular logistic regression and cumulative logistic regression, which is a nice model if you have ordinal response data. This is not a very popular model, so I have illustrated what that model form is here. And the other thing we do in Diamond is we use some quasi-Newton optimization techniques from a paper by Thomas Minka. Okay, but Diamond is not the only way to fit models like this. I gave some examples before using stats models. But mixed effects models have a very Bayesian sort of flavor. And so that's another approach to fitting these kinds of models. So maybe I've convinced you that mixed effects models are worth considering, and you want to try fitting them. Here are a few ways that you might go about doing that. If you want to embrace the fully Bayes paradigm, you can do Markov chain Monte Carlo sampling, which is a perfectly good approach, and there are a number of good Python packages for doing this. You can use Diamond if you are willing to specify your hyperparameters somehow. Stats models will fit some simple mixed effects models, but only for linear regression and only for one grouping factor. Or if you're willing to use R, you can use LME4. But this can be awkward if your production pipeline is Python, 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 Python. It's awkward to splice R in the middle. So And these are sort of, I call these exact methods. I mean, they're all really approximations because there's no analytic solution. But these are attempting to solve really the problem that you want. There's another class of methods that solve a problem that is hopefully close to your original problem. So for example, in the full Bayes paradigm, variational inference allows you to write down a fully Bayesian model, and it doesn't fit that exactly, but tries to find a solution which is close to that in some sense. Likewise, there are some moment-based methods for fitting mixed effects models that come up with an approximate solution very quickly. And it's not solving exactly the problem that you want to solve, but hopefully it's solving something that's close enough. And another thing that you might try, for mixed effects, because all of our parameters are, or most of our parameters, are assumed to be drawn from normal distributions, this works out to a pretty complicated form of L2 regularization. And in particular, what you get is this sort of very big, sparse, block diagonal penalty matrix. And instead of doing that, because it's a huge pain in the neck, you might just approximate that matrix with the identity matrix times some scalar. So in other words, don't do all this complicated stuff, just use simple L2 regularization on everything. So I have some results for that. So I guess to compare these methods, I implemented a few of these methods on the movie lens data set. And I picked the big one, which has 20 million observations. And there are ratings, explicit ratings of movies by users. And although rating is really ordinal, I decided to binarize it because all of the methods I am comparing are, they all support logistic regression. They don't all support ordinal logistic regression. But I will say again that if you want to honor that your response variable actually is ordinal, then Diamond does support ordinal logistic regression. And I'm just going to fit a very simple model that learns bias terms for every user and every item. Okay, so to do this in Diamond, you import the logistic regression module, and we input sigma, our covariance matrix, as a data frame. And let's see. So we have an intercept for every user and every movie. And this awkward structure is actually straight from LME4. But for this example, I just input it by hand. And we see that the variances are pretty close to each other, 0.9 and 1. And then we instantiate our model, and then we fit it using this formula notation. Diamond is an iterative method, so we specify a tolerance and a maximum number of iterations. Okay, so how long did that take? So first of all, to learn this covariance data frame, covariance matrix, I took a 5% sample of the movie lens data, and I fit it in our LME4, which took an hour. And then to estimate the coefficients for the full data set, all 20 million observations, it took about 83 minutes to fit on my garden variety MacBook Pro. In comparison, I used scikit-learns to do simple global L2 regularization. So I just used cross-validation to pick one regularization parameter, which took 24 minutes. Grid search might be a fair comparison because here I have learned 2 parameters which are used for regularization, whereas down here I've only learned 1, but that's okay. And then scikit-learn is nice and fast. Fitting it only takes a minute. But you wonder, like, okay, but this is not right. As I said before, Diamond is solving the exact problem. This simple global L2 regularization is solving a problem that might be close to that problem. Kind of hard to say. So let's compare the predictions that the 2 models output. And lo and behold, they're pretty similar. And scikit-learn is much faster. But I think this is somewhat of an artifact of the movie lens data set. In particular, the fact that our variances are so similar means that approximating these two numbers with one number is a pretty good approximation. So if you had more features or much different variances, I think this approximation would not be as good. If you tried to fit all 20 million observations in our LME4, I tried that. It took more than 6 hours, so I gave up. So I don't know, maybe your patience is greater than mine. But when I say that LME4 does not scale well with the number of observations, this is what I mean. There's also an active area of research into using the method of moments to estimate these kind of models. And there are professors at NYU and Stanford and maybe elsewhere that are working on this. And you can use these techniques to fit kind of simple models. So models maybe with one group and some features, or no features but two groups, or but currently, as of today, there are no moment-based methods for fitting multiple groups with features. But to give you some idea of the performance, let's see. I fit this model on the 20 million movie lens data, and it took 4 minutes. So I'm not sure exactly what my patience is, but it's less than 6 hours, but 4 minutes is adequate. That's fast enough for me. I also tried fitting this model. This is the same model that's learning user and item biases. Using Edward. Edward has a black box variational inference functionality, which I will admit I do not understand very well, or really at all. And this fit in under 5 minutes, so I think variational inference is very exciting. And I think there are some talks at this conference about fitting Bayesian models, and maybe some that will cover variational inference. So if I will be at those, maybe I will see you there. Okay, so I ran through a bunch of examples, and I think in none of them did Diamond outperform the comparison. So you might be wondering, why should I use it? So let me give you some qualitative reasons why you might consider using it. Compared to Markov chain Monte Carlo sampling or LME4, it does scale well with the number of observations. So I was able to fit a simple model to 20 million observations in a reasonable amount of time. It does solve the exact problem. So compared to variational inference or moment-based methods, it's really solving it's solving the exact problem, not an approximation of the problem. And this could be more or less important depending on the problem and how strict you are. It scales okay with a number of features compared to simple global L2 regularization. And as I mentioned before, it supports ordinal logistic regression. So if you want to honor your response variable and its ordinal nature, Diamond supports this. So I hope I have convinced you that mixed effects models are useful for recommender systems and other applications of data science. There are some computational challenges, and they can be hard to fit to large data sets. But there are some good approaches for doing so, which include Diamond, the package that we wrote, the moment-based approaches, and variational inference. And also, you don't have to choose. You can use mixed effects models in conjunction with whatever models are your favorites or that you're already using. That's all. Questions? Comments? Yes. Mm-hmm. I do. I didn't include it in this presentation, but on Kaggle right now, there's a competition for music recommendation for a service called KKBox. So I've been doing some experiments using XGBoost to learn feature interactions about users and items, and then using mixed effects models to learn the user and item biases. I think that the parametric specification of those bias terms is a better way to learn them than the kind of like one-hot encoding you might learn in XG, in an XGBoost kind of model. Yes. I'd be happy to do that. So what this represents is how different the users and the items are from each other. So I can give you, so in the Kaggle data set that I was just talking about, I guess what this represents is so the variance term for users or for items just represents what the spread is between them. So if all of the movies are have the same popularity, then the variance will be very small, close to zero. But if the users, have like wildly different levels of pickiness, like some people just always hate everything, and some people always love everything, that will be a very large variance. So for the KK-box data set, the variances are like an order of magnitude different for users and for in that example, in that data set, it's songs. Yes. Let's see. That's a good question. I would say that if you're interested in doing inference on models like this, that the way to do it is through a fully Bayesian perspective, and probably doing like MC sampling. If you just want to find like the maximum a posteriori estimates, variational inference, well, actually, certainly Diamond will give you that. Diamond does not give you the standard errors. But I think that that a fully Bayesian way of fitting is advisable if you're interested in doing inference. Yes.
In your example, the model had data set that was distributed over the groups. Does Diamond support a model where the slope is?
Absolutely. You can have all kinds of varying slopes and intercepts as complex as you like. Yeah. For this example, I just let the slope vary because, sorry, I just let the intercept vary because I had this intuition about, different silhouettes need to have different lengths. Maybe there's some reason that the way that height affects the ideal length of genes also varies by silhouette, but I didn't have much intuition about that. But you could certainly fit a model like that, which would give you lines with varying slopes as well as different intercepts. And Diamond certainly supports that. Yes?
So this example is great and very interpretable. Do you find that when you add more features in that are predicting, let's say, full recommendation scores, are you still able to interpret the results?
Yes. Yeah. So I would say that's a nice advantage of using something that's built on linear models, because what you'll get if you have more features here, if you have more features if you're learning a bunch of slopes for each silhouette, let's say, what you'll get is a vector of coefficients for every silhouette. And then you can look at those and visualize them and make some nice plots of them. So it does give you, like, this is still linear models. You do get coefficients on features that you create. So I would say in that sense, yeah, what you get is still pretty interpretable. I would also like to mention that since they're built on linear models, it's easy to serialize them and put them in production. Because for making predictions, you're just doing a dot product of a matrix of coefficients and some vector. So it's easy to productionize models like this. Yes? Great question. I'm really glad you asked that question. So what happens in that case, yes. So the question is, what if you have like just a user who has only rated one thing? Does this throw it off? So you could fit, So yeah, what happens if you don't use any regularization and you just fit a straight linear model, what you will get is you'll be able to predict that user's one rating perfectly because you can overfit it exactly. So what mixed effects models do is for small groups, in this case, a user who only has one rating, the regularization will pull them so that their prediction is more like the average prediction for all users. Or in this case, in a model like this, because our user bias terms are drawn from this normal distribution centered at 0, the estimate for that user will be pulled towards 0. And as the optimizer trades off the penalty with the loss function, there's not much gain to be had. It doesn't decrease the loss very much for that user to have a large value, but it does increase the penalty a lot. So mixed effects models learn to kind of trade off, starting from the global average, and then with more observations, letting users or items behave in their own way. So, and I think this reflects kind of the intuition that many of us have, that if you know nothing about a user or an item, it should behave like the average. And then as we observe it more and more, we'll allow it to behave in its own special way. Last chance for questions. Yes? I didn't. It's a good question. So the question is about performance with more complex models in terms of number of observations. I'm not sure. Certainly, there's some advantage to having like this sort of rigid parametric model form, but I did not measure that. Right. Thanks again, everyone.